Now let's learn why neural networks need non-linearity. Okay, so the learning objectives here include the following: that by the end of this lesson, you should be able to explain why linear models are insufficient for many real-world problems. I mean, we already saw that. I mean, we ended the last video on that note that so a single perceptron will not be able to solve certain problems. So we need multi-layers of perceptrons. So that's ML, multi-layer perceptron. So you'll be able to explain why linear models are insufficient for many real-world problems. Understand the role of activation functions in neural networks. We already saw that a little bit in previous videos, especially the last one. Then you explain why stacking linear layers without nonlinear activation is ineffective. So even multi-layer perceptron has its own issues, right? Just stacking linear layers without nonlinear activation can be problematic. Understand the mathematical intuition behind nonlinear transformations. So we started out with linear transformations, talking about weighted sums. Then also describe and implement common activation functions like sigmoid, ReLU, and explain why nonlinearity gives deep learning its remarkable power. So let's talk about the introduction now. So deep learning has revolutionized fields like computer vision, natural language processing, NLP, speech recognition, robotics, and medical diagnosis. So a common misconception is that neural networks become powerful simply because they contain many layers. In reality, the secret ingredient is nonlinearity, not multiple layers, right? Without nonlinear activation functions, a neural network with hundreds or even thousands of layers behaves exactly like a single linear model. Understanding why this happens is one of the most important concepts in deep learning. So let's see all of that. So let's start with linear models that we are familiar with, talking about linear transformations and all of that. So it's a linear model computes an output using y equals wx plus b, where w is the weight matrix, x is the input vector, and b is the bias vector. So the output is simply a weighted sum of the inputs plus a constant bias. So the output is simply a weighted sum of the inputs plus a constant bias. Now imagine an example. Suppose y is 3x plus 2. So if x is equal to 4, then 3 times 4, so now that x is 4, so you have 3 times 4 plus 2, which is 14. This relationship forms a straight line because y is 14. So the properties of linear functions now include the following. Linear functions have several important characteristics. They produce straight line relationships. They have a constant slope. They cannot represent curves. They cannot model complex interactions among variables. For example, house prices depend on many interacting factors such as location, neighborhood, school quality, age of the house, market conditions. Of course, this is the American setting. So these relationships are highly nonlinear and cannot be accurately represented using a single straight line because you have multiple factors. Now, the question is another question is why multiple linear layers do not increase model power. So from the last video, we saw that, oh, okay, a single perceptron may not do the job. Maybe we need layers of that. And that's why we talked about multiple layer perceptron. So why multiple linear layers do not increase model power? Suppose a neural network has two layers without activation functions. The first layer computes H is W1X plus B1, and the second layer computes Y is W2H plus B2. Substituting the first equation into the second gives this that y is equal to w2 of w1x plus b1 because that's h, right? Plus b2. So if you expand all that, you have y now is w2 w1 multiplied by x plus w2 b1 plus b2. So then we can define that we have a w prime, which is w1 w2, which is still like the normal weight we used to know, and then b prime can then be the weight attached to B1 plus B2. So technically, Y is still like a weight matrix multiplied by an input vector plus a bias vector. This is still just a single linear equation. No matter how many layers are stacked together, the entire network remains equivalent to one linear transformation. So that's why even multiple layer does not do as good a job as we would imagine. So suppose we now have layer 1 to be 2x plus 1. Layer 2 is 5h plus 4. Substituting now, we have y into 5h, that h being 2x plus 1 plus 4. So if you multiply it, you have 10x plus 5 plus 4. So y is 10x plus 9. So instead of having two separate layers, we have simply produced another linear equation. So multiple layer doesn't help so much. So in that case, now you see that whether we do them separately or we stack them together as single layer, you end up getting 39 for each. So imagine you define layer 1 as 2x plus 1, layer 2 as 5x plus h, and x is now 3, right? So we define x to be 3. Now, you know that will be 10 times 3, 30 plus 9, that's 39. So when you do that, if you do the network output, so you have layer 1 into layer 2 as a function of layer 1, right? So this is layer 2 as a function of layer 1 here. So that's line 9 giving us that. And then the next one, you have a single layer output, which we already know we get by taking the function of a function, we get 10x plus 9. So you see both of them give us exactly the same value, 39 each. So both outputs are identical. This demonstrates an important fact that linear plus linear will always be linear. So if you have 1 billion linear stacks, you end up getting a linear one a linear system at the end of the day. Therefore, stacking linear layers alone does not make a neural network more expressive. And that introduces the idea of nonlinearity, which this video is really about. Now, suppose we introduce an activation function, say the first layer becomes h equals f of w1x plus b1, where f dot is a nonlinear activation function. So, of course, f can actually be a linear activation function, like when you have a step function or something like that, or some other functions that are linear. But if it is a nonlinear activation function, that's our interest here. So the second layer becomes like the y equals w2h plus b2. So if you substitute now, we have y equals w2 instead of it just swallowing up w1x plus b1, we still have this function coming together here. So we have w sub 2 f of w1 of x, w1x plus b1 plus b2. So since the activation function is non-linear here, this equation cannot be simplified into a single linear equation. So this allows neural networks to learn highly complex relationships, which some serious real life data sets represent. So the intuition is that imagine folding a flat sheet of paper. Without folding, the paper remains flat regardless of how many times you slide it around. However, repeated folds allow the paper to form complicated three-dimensional shapes. Activation functions perform a similar role. Like activation functions are that they help you to fold your paper in different forms so that you can get, like, from a plain paper you can get a cuboid, you can get a cube, you can get all those three-dimensional shapes. You can get a cylinder, very simply. So they bend the feature space, allowing neural networks to model linear relationships. Now, what is an activation function then? Every neuron first computes z equals wx plus b. That is a weighted sum. So instead of returning z directly, the neuron applies an activation function a, which is f of z. So this activation function transforms the linear output into a nonlinear one because f would usually be nonlinear. So without this transformation, deep neural networks would simply behave as linear models, which are not always interesting. So why activation functions matter then? Activation functions allow neural networks to learn curves, nonlinear decision boundaries, feature interactions, hierarchical representations, and complex real-world patterns. Without activation functions, then deep learning would not exist. So activation functions make all the difference, between just linear expressions and deep learning. So let's talk about sigmoid activation function. That's a type of activation function which is nonlinear. So the sigmoid function is defined as sigma of x, which is 1 over 1 plus e raised by minus x. The sigmoid function maps every real number into the interval 0, 1. Right? So if you put any value you put here for x, you always get something. In fact, I think I've talked about it in a previous video. You have 1. So let's say you have f of x, which is, or f of x, which is 1 over 1 plus e raised by minus x. So what happens here? So at x equals 0, so you see that f of x will be 1 all over 1 plus e raised by minus 0, you know, e raised by minus 0. That is 1 all over 1 plus 1 over e raised by 0. So that is 1 all over 1 plus e raised by 0 is 1. So we have 1 all over 1 plus 1. And that means we have 1 all over 2. And that is simply 0.5. So we have at x equals 0, we have 0.5 for the sigmoid function. So on the other hand, if we have, let's imagine that we have, so we've done 0, right? 0 gives us 0.5. So what if we have minus infinity. Okay, so f of minus infinity would be something like 1 over 1 plus e raised to power minus, then x is now minus infinity. So that's 1 over 1 plus e raised to power infinity. So that's 1 over 1 plus e raised to power infinity is infinity already. So that's 1 plus infinity. That is 1 all over 1 plus infinity is infinity. And 1 over infinity is simply 0. So it means that we have minus infinity for x gives 0 for sigmoid. And then lastly, we have infinity itself. So f of infinity, that will give us 1 all over 1 plus e raised to power minus infinity. So in that case, we then have 1 all over 1 plus e raised to power infinity is like 1 over e raised to power infinity. E raised to power minus infinity is the same thing as 1 over e raised to power infinity. That's 1 all over 1 plus 1 over e raised to power infinity is infinity. So that is 1 all over 1 plus 1 over infinity is 0. So we have 1 over 1. So which is simply 1. So here we see that infinity and infinity corresponds to 1 for the sigmoid function. So what do we have? For list everything we have, then it means we have for minus infinity. So minus infinity goes with 0, then 0 gives 0, which is at the center of minus infinity and infinity, leads to 0.5, and then infinity itself leads to 1. So whatever happens, you always get values between 0 and 1 for the sigmoid function. So the sigmoid function maps every real number into the interval 0, 1. So this makes it useful when outputs are interpreted as probabilities like that. So we then have probabilities of sigmoid. They are smooth and differentiable. Output ranges between 0 and 1, like I've shown you, from negative infinity to positive infinity. And there are no, in fact, 1 plus e raised to power minus x, if we equated that to 0, I mean, it's smooth. In short, there are no discontinuities, basically. So commonly used for binary classification output layers and suffers from the vanishing gradient problem for very large positive or negative inputs. So you can see for very large negative values, it vanishes. For very large positive values, you just get 1 like that. So suffers from the vanishing gradient point for very large positive or negative inputs. So for example, suppose x is 2, then sigma of 2 is 1 over 1 plus e raised to power minus 2. So that means you have 0.135. So sigma of 2 then, oh, sorry, e raised to power minus 2 is 0.135 rather. So everything together, sigma of 2 is 0.881. That's like 88.1% of, of predicting the right result. So we can also do that using Python. So import NumPy as NP. So then you define sigmoid function to be 1 over 1 plus exponent e raised to power minus x. And then try that for different values, from -5 to -2 to 0 to 2 and 5. So of course we know 0 will give us 0.5. And then so for -5, we have 0.00666928. For -2, we have 0.11920292. For 0, we get 0.5. For 2, we get 0.88079708. And for 5, we get 0.99330715, like that. So it's guaranteed that it will always be between 0, from 0 to 1 rather. So the advantages include that it is smooth and differentiable and interpretable as probabilities. The disadvantages of sigmoid function include that for very large positive or negative inputs, the sigma, the x, becomes extremely close to 0, right? So that's what you can see here, that for positive infinity, for negative infinity, you have 0 here, and this is 1 up here. So for large positive or negative inputs, this becomes extremely close to 0. So a gradient approach 0. As gradient approaches 0, learning becomes very slow in that case. So this phenomenon is called the vanishing gradient problem. I think we looked at that in some videos, an earlier video before this. So another kind of activation function, which we even talked about in the opening video, is this rectified linear unit function. Rectified linear unit. So the ReLU stands for rectified linear unit. It is defined as ReLU x, which is the maximum of 0 and whatever value you supply. So maybe after computing your weighted sum, the ReLU computes, it takes the one that is bigger between 0 and that value. So if your weighted sum is negative, then the answer will automatically be 0. Then if it is positive, then it will be the weighted sum with the answer. So if the input is negative, the output is 0. If the input is positive, the output equals the input itself. So example, if you have x is -5, the value of -5 is simply 0 because -5 is between 0 and -5, 0 is bigger, so you take 0. If x is 7, the value of 7 is 7 because 7 is bigger than 0. That's the rectified linear unit. Now, import NumPy as NP now. So we can, I mean, this is what we did the other, what we did for Sigmoid function, we are doing for the rectified linear units now. So we define the function ReLU of x as returning the maximum between 0 and whatever x is supplied. If we now take values to be np.array -5 -2 0 0 2 5. So print ReLU values now. So here you have, so for minus everything negative, all the answers will be 0. For 0, between 0 and 0, 0 is still the bigger. So you pick 0. So for 2 and 5, 2 and 5 will automatically be the answer. So let's see, for this activation function, what are the advantages of the rectified linear unit? Of course, it is extremely simple. You just take the maximum between 0 and whatever value you supply, and it is computationally efficient, and it helps reduce the vanishing gradient problem and allows deep networks to train much faster. The default activation for most, it is the default activation for most hidden layers, right? So for most AI issues, for most AI problems or machine learning problems that involves activation function, except you specify what exactly you're using, the rectified linear unit is the default one that is used for most hidden layers. So what are the disadvantages of the rectified linear units? So for x less than 0, the output is always 0. So there's no difference between anything from 0 down to -1 million or minus infinity. The answer is always 0 in that case. So if a neuron continually receives negative inputs, its gradient becomes 0 and it may never recover. This issue is known as the dying ReLU problem. So the other time we talked about the vanishing gradient problem associated with the sigmoid activation function. But for the ReLU activation function, we have the dying rectified linear units problem. So because the gradient becomes 0 for too long and it doesn't ever get to bounce back. So comparing sigmoid and ReLU now. So imagine the output range. So the output range for sigmoid is 0 to 1, and for ReLU it is 0 to infinity. So everything negative infinity is cut off. So ReLU is from 0 to infinity, and then for smoothness, sigmoid is smooth, but ReLU is not smooth. At x equals 0, there's a jump. The computational speed, sigmoid is moderate. ReLU is very fast because it quickly makes decision which is bigger between 0 and whatever you supply. Then you have vanishing gradients attached to sigmoid, but it is mostly avoided for ReLU, for the rectified linear unit, that is. For the common usage, sigmoid is the output layer, while ReLU you have them in hidden layers. So with and without activation, and let's look at some example with and without activation. Imagine that x is equal to 2, and the first layer computes z1 equals 3x plus 1 equals 7. So without activation, the second layer then computes y equals 4z1 plus 2. So therefore, y is equal to 4 multiplied by 7 because z1 is 7 plus 2, and that is equal to 30, right? So this is equivalent to y equals 12x plus 6. Y equals 12x plus 6, which is still linear for sure. But if you use the rectified linear units, the activation becomes AI, which is ReLU 7. So ReLU 7 remains 7. So the second layer then computes y equals 4a plus 2, which is 30. So if you now consider x to be -2, so z1 will be -5, and 4 times -5 is -20 plus 2, that's -18. So with ReLU, you discover that a1 here can be 0. A1 is 0 because we have filtered out this. So if A1 is 0, then that will give us Y, because A1 is 0 here, Y will just automatically be 2. So the activation function changes the network's behavior dramatically, allowing it to represent piecewise nonlinear relationships. So you can already see the effect of ReLU, which is a very simple activation function, by the way. So once there's negativity, it already knocks out that part and it leaves us with only the bias. Now, why deep learning works? Deep neural networks progressively transform raw data into increasingly abstract features. So for image recognition, a typical hierarchy is you have the pixels, you have the edges, you have the corners, the shapes, the object parts, the complete objects, and the categories. And then each layer lends a more sophisticated representation than the previous layer. This hierarchy is only possible because nonlinear activation functions transform the feature space after every layer. Now, let's talk about some applications of nonlinear neural networks. Nonlinear neural networks are widely used in computer vision for face recognition, medical imaging, object detection, and autonomous driving. We have a lot of autonomous cars these days. So you have that. Then natural language processing. You have you know, neural networks used in natural language processing for machine translation, chatbots, text summarization, and sentiment analysis. Then you have them used in speech recognition for voice assistants and speech-to-text systems, and for recommendation systems like movie recommendations, product recommendations, music streaming services. In healthcare, you have them used for disease detection, cancer diagnosis, MRI, and CT image analysis. Then in summary, we have that a linear layer computes a weighted sum of its inputs. Then stacking multiple layers still produces a linear model at the end of the day. So activation functions introduce nonlinearity into neural networks, and nonlinearity enables neural networks to learn complex patterns. The sigmoid activation maps outputs to probabilities but can suffer from vanishing gradients, while the rectified linear unit is computationally efficient and is the most widely used activation function in hidden layers. So deep learning derives its remarkable power from composing many nonlinear transformations across multiple layers. And then that takes us to the practice problems, of which I get to solve two. So here you can see, let's see, how many can you see together? You can see problems 1 to 6 right here. And I'll be taking care of problems 3 and 10. So I'll be taking care of 3. Assume a neural network computes y equals w2 into w3 into w2 into w1 of x. Assuming there are no activation functions or biases, prove that the network is equivalent to a single linear transformation. So when you stack many linear transformations together, you end up still getting a linear transformation. So I'll be solving that. Then I'll talk about I'll also solve question 10. But here you can see problems 1 to 6 right now. Then okay, okay, I'll still show them later. Then this is you can see 7 to 18 clearly here. 7 to 17. Then I'll be taking care of 10 also. It says describe the vanishing gradient problem and explain why it slows neural network training. Okay, I'll be talking about that too. Then you can see the rest of the problems now. Okay, so let's go and deal with the problems as we bring this to a close gradually. So let's start with problem 3. Problem 3. A a neural network computes y equals w3 into w2 into w1 x. Assuming there are no activation functions or biases, prove that the network is equivalent to a single linear transformation. So the solution to problem 3 now, starting with the given network, we have y to the w of 3 into w of 2 into w1 of x. That's the function of a function of a function. So using associative, using the associative property of matrix multiplication, we have y to be W3. We have y to be W3, W2, W1, all of x. So if we let W to now be W3, W to W1, then y can simply set to be Wx, which is simply a linear transformation, straightforward. So this is exactly the equation of a single linear transformation. Therefore, regardless of how many linear layers are stacked together, the entire network behaves as one linear layer. So in conclusion, without nonlinear activation functions, increasing the depth of a neural network does not increase its ability to learn complex patterns. And that goes. So then we move on to problem 10. Problem 10. Describe the vanishing gradient, problem, and explain why it slows neural network training. Okay, so we go on with that solution. So during training, right? During training, neural networks update their weights using gradients obtained through back propagation. So then, for the sigmoid activation function, for the sigmoid activation function, sigma of x is equal to 1 all over 1 plus e raised to minus x. Its derivatives its derivative is sigma prime of x, which is equal to sigma of x into sigma of x into 1 minus sigma of x, like that. When you differentiate this expression, so there, the largest possible value, largest possible value of this derivative is 0.25. And for very large positive or negative inputs the derivative becomes very close to zero, So during back propagation, gradients are multiplied together across many layers. So suppose four hidden layers, each produce a gradient of approximately 0.1. The gradient reaching the earliest layer becomes 0.1 times 0.1 times 0.1 times 0.1, which is 0.0001, like this. This value is extremely small. This value is extremely small. As a result, weight updates become tiny. So the weight becomes smaller, very small too. Then next, earlier layers learn very slowly. Earlier layers learn very slowly. Next, training may require many more iterations. Then in very deep networks, learning may almost stop. Learning may almost stop. This phenomenon is called the vanishing gradient problem. The vanishing gradient problem. So modern deep neural networks largely overcome this issue by using activation functions, by using activation functions such as ReLU, whose gradient is d dx of ReLU of x, which is 0 when x is less than 0 and 1 when x is greater than 0. So for positive inputs, the gradient remains equal to 1. Allowing information to flow backward much more effectively during training. Yes, and that is exactly what we have there. So we go back to the problems. Again, I'll just show them once more. So you can see problems 1 to 7, all of that here. Problems 1 to 7. Problems 1 to 7. Then 8 to 19. In fact, everything else. Now you can see 8 to 20. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, what exactly are you waiting for? Why not go ahead and subscribe right now? Hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges that you find out when you click. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.